Hi, I'm Tanish, and this is Basics of Probability Part 2, Experimental Probability and Geometric Probability. First up is experimental probability. Experimental probability is based on repeated trials in an experiment, and the number of trials in the experiment is how many times the experiment is performed. The formula is number of successes over total number of trials. So if I have a spinner and I spin it around, spin it once, that's a trial, right? And the number of times I spin it around is basically the number of trials I do it. And let's say I want to see the outcome on how many times blue comes after spinning it a certain amount of times. That means you have to use the formula number of successes over total number of trials, with number of successes being how many times I get blue. Let's try an example. Let's say we have this spinner over here, and each section of the spinner has the same area. That means it's equally likely to land on any of these sections, blue, yellow, purple, etc. And let's say we spin the spinner 50 times. For which color of the experimental probability is the same as the theoretical probability? So what we're learning is experimental probability, which is based on the number of times you try it. What theoretical probability was in the previous video. If you have not watched that already, I have the link in the description. We learned theoretical probability in the previous video, and what it means is it's the probability of each of these outcomes happening. And since all of these can happen equally, that just means since there are five of these, it's it's a 20% possibility for each of them. So it's 1/5, which is the theoretical probability. So if we were to spin it 50 times, 1/5 of 50 times would be 10. So let's spin this spinner. I spun the spinner 50 times, and these are the results I got. I also noted what the number when I spun it 5 times, 15 times, and 30 times. These were the outcomes I got for each of them. And I did this to prove something really important, right? The more trials I have in an experiment, the closer the experimental probability comes close to the theoretical probability, right? And we'll see once I show you. So if I spin it 5 times, right? And since the probability of each of these landing on each of them is 1/5, right? That means the theoretical probability is that it'll land on each of them one time. And if you look here, when I spun it 5 times, only one of them got it landed on one. Only one of them matches the theoretical probability, right? But when I spin it 15 times, it'll be 15, and that means 3. So it should land on each of them 3 times. That's the theoretical probability. It should land on each of them 3 times. And over here, it landed on 3 only twice. But it's a much bigger improvement from the previous time, right? Where there was only one that landed, the experimental probability matches the theoretical probability. And now for 30 times. 30 is equal to 6. Alright. Although we have only one that matches where the experimental probability matches the theoretical probability, but all of these other things are kind of close to 6, right? Previously they were quite far off, right? All of them were quite far off. But the more trials we do, we get closer and closer to the theoretical probability. So if I do like a number really high, we should eventually get a clean slate where each of these is just 1/5 of the total trials, right? So for 50 rounds, I got this 14, 10, 8, 8, and 10. Now let's solve the actual problem, which is how many of these matches the theoretical probability. So since I have 50 times 1/5, so each of them have it'll be landing on 10 of them on each section. And over here, only two of them match. So the answer to our question was 2. But if you look at these two numbers here, they're also quite close to 10, right? So we're getting somewhere. All of these numbers are coming closer and closer to the theoretical probability. If I choose a really high number like 1 million, I spin this 1 million times, then I should be getting a very close number to the theoretical probability. Now we have geometric probability. And geometric probability is based on calculating ratios and lengths, areas, and volumes. So let's say I have this dartboard and I'm able to hit any point on this dartboard equally. I can hit here, here. All of that is an equal probability. And I'm so good at throwing darts that whenever I throw a dart, it always hits the inside the dartboard. So what is the probability of my dart hitting one of these two sectors in this small circle? This problem is to scale. So the distance from here to here, which is the radius of the small circle, is 2. The distance from here to here, the side of the square, is 10. Right. So what we have to treat this like a probability problem because that's what this is essentially what it is, right? So this is our favorable outcome, these sectors, all over the total outcomes, which is the entire dartboard. So the area inside the sectors over the total area. Let's do the total area first. Since this is a 10 by 10 square, this area is 10 times 10. And now we have to find the area of these sectors. Let's first do the area of one sector. Area of one sector is pi r squared times theta over 360. Theta is just this angle over here for the sector. And the angle over here is 90 because there are 4 sectors. And since it'll be 360 divided by 4, this will be 90 over here. So that will be and r will be 2 because it is given here. All right, so let's solve that out. And we cancel those, we will be left with pi. So the area of one sector is pi. And since we have 2 sectors, you have to multiply this by 2. So it's 2 pi. 10 times 10 is 100. So we have 2 pi over 100, which is equal to pi over 50. This is our probability.